Let's get started. The first thing is the first competition, the deadline is next Sunday. So you have to start your competition before next Sunday. I think it's Sunday midnight, you have to start. So if you are in the elementary group, you only need to answer 30 minutes short questions. There are like 5 questions you have to answer. And if you are in the middle school or high school division, you have 30 minutes short question and you have a coding assignment. The coding only one coding assignment, and you have 72 hours to finish. Okay, you have 72 hours to finish. So you should receive 2 emails. If you are middle school and high school, you should receive 2 emails. And for elementary school students, you should receive only 1 email. Okay, so there is a link. So you just click that link, and I think the link will bring you to a website called HackRank, and you can use your email to register on the HackRank. And then after you click the start, you have to finish within either 30 minutes for the short question or 72 hours for the coding assignment. Okay, so the first competition has 2 major topics. Actually like three major topics. The first topic is the number system, which we discussed last week. Okay, the second one is the topic we are going to go through today. It's called recursion. And the third one is some basic coding concept. It's like if else or something like the for loop. It's very simple. It's not so difficult. Okay, so I'm not going to the details about the coding assignment, but I'm going to go through the recursion today. All right, so let's get started. First, this is today's goals. This is the open session, and we have elementary school students to high school students. So I'm going to really quick go over algebra first for the function. What is a function? And then we are going to our main part, which is the recursive functions. And there are several advanced topics. I don't think I have time today to go over those advanced topics, including the subsets, commutation, combination, and the backtracking. So this is kind of advanced topic in the recursion. I'm not sure. I don't think I have time today, but if you are interested in, you can do some research or do some read some articles or coding by yourself. But I just give you some idea after the recursion what you can do further. Okay, and today's the most important goal is we can ace the ACSL contest 1. All right, so let's get started. There are several resources. I shared these resources with you last week already. So actually, the third one is very useful. Oh, I should update this. So it's not a number system. It's about the recursion. Okay. Okay, so let's go over the algebra. What is a function? So the function is actually just an equation that has only one answer for y, for every x. Okay, I think this is like maybe middle school, 7th grade or 8th grade algebra function. Okay, so in math, we usually use fx, gx, or hx, etc. to represent a function. Usually it's only like one letter, f, g, or h to represent a function. Okay, so for example, f2 means when x equal to 2, right? The f2, what's the value for this function? Okay, so this function will take x equals 2, and we are going to calculate. So for example, fx equal to x plus 7. So if x equal to 2, then we have fx equal to 9, right? So this is very, very simple. So even elementary students should understand this. Okay, so this is we just spend like 1 or 2 minutes to go over the algebra. Okay, and now it's coming a little bit more complicated. It's called the recursive function. So what is the recursive function? So in math, the recursive function is a function that repeats or uses its previous term. So you have to pay attention. It's like uses the previous term to calculate the subsequent terms, and this forms a sequence of terms. So there are like 2 types of forms in math. For example, this is the first form, and this is the second form. So let's look at it each one. So the first form is like a1 equal to 1. So I'm going to give you the first number, which is a1. a1 is equal to 1. And then I'm giving you a formula. So this formula defines an is equal to an minus 1 plus 4. So basically this n can be what? Can start from 2, 3, etc. right? So the n can start from 2, 3, etc. So what I can do is A2 is equal to what? Is equal to A1 plus 4. So what this number is? A1 is 1 plus 4, which is 5, right? And then A3 is what? A3, then now n is equal to 3. And this one becomes to A2 plus 4, which is becoming to 9, right? And I'm writing one more. A4 is equal to A3 plus 4, which is 13, right? So we can calculate this sequence calculating something like this, right? But when we define this recursive function, we do not need to define A2, A3, etc. We only need to define what does this call. Anybody know what does this call? The first term. So the first term is called the base case. In computer science, we call that in the base case. Okay, we define the first term, and then anything else like A2, A3, A4 can be derived from A1. So anything else can be derived from A1. Okay, so remember it's used the previous term. So when we calculate A2, we use A1. When we calculate A3, we use A2. So everything is using the previous term. Okay, so this is the first notation. Or we can change an plus 1 equal to an times plus 4. That's the same thing. That is almost the same thing. So this is the first notation. And the second notation is we define f1. f1 equal to 1. Okay, so this is also our first term. f1 equal to 1. That means when x equal to 1, this f1, actually we can see f at y then f1, right? Or we can see like y equal to 1 and our y n, or you can write something like this. Okay, this is the first term equal to 1, and my fn is equal to fn minus 1 plus 4. Okay, so this is another term, which is the same thing. And when n equal to 2, so my f2 is equal to f1 plus 4 is also equal to 5. Okay, my f3 is equal to f2 plus 4, which is equal to 9, etc. Right? So this is the recursive function in math. This is recursive function in math. So it's very similar for the recursive function in computer science. So we are going to do some coding later in a few minutes. So let's do some more math exercise. So I have a sequence 10, 15, 20, 25, 30, 35. Can you find a recursive formula for this one? Can anybody find a recursive formula for this one? Anybody? So you can type in the chat. Yeah, I got some correct answer. So remember, when you define the recursive formula, we always need has a base case. Okay, we need to define f1. So f1 is equal to what? f1 equals to 10. Okay, and after this f1 equal to 10, we have our fn. Okay, our fn equal to what? Is equal to, you can see this is plus 5, right? Because it's like increased by 5 for every sequence, for everyone, for every sequence, for every number, right? So basically, I define a base case, f1 equal to 10, and this is my recursive formula, right? This is my recursive formula because this one is using the previous term. This one is using the previous term. So you can try. f2 is equal to f1 plus 5, which is equal to 15, right? And my f3 is equal to f2 plus 5, which is equal to 20, etc., right, etc. So then I can generate this sequence by define this recursive formula, right? So don't forget the base case. Don't forget the base case. This one only is not a recursive function because what? If you define something like this, what happened? If you define something like this, what happened? Anybody know? If you write some code, like either Python code or C++ code or Java code, if you write some code like this, what will happen? If I call F100, what will happen if I have some formula this?
Some students reply error. No, it will not give you error.
It would take too long, I think.
It will take, yes, it's repeat forever. It's called infinity loop. It's called infinity loop. Eventually, it will give you error. Eventually it will give you error, but this error is because you're out of your memory. Okay, your computer has limited resource. Your memory, your RAM, your memory, your computer memory is a limited resource. Okay, and when you call this, it will create room. It will occupy the memory, and eventually your memory is like you use all your memory, so you're going to get out of memory error. Yes, it eventually will get some error, but it is actually a infinity loop, because when you reach to F2 is equal to F1 plus 5. And then you have to calculate F1. Then your F1 is equal to F0 plus 5. And then you have to calculate your F0. Then your F0 is actually equal to F minus 1 plus 5. So you do not have any like ending situation, right? It's like taking forever. So it's infinity loop. It's something like infinite loop. If you write some code, it's actually just something like this, while true. Okay, it's just something like this, while true. It runs forever. Okay, so this is something you have to pay attention when you define recursive formula. Don't forget your base case. This is your base case. All right, so let's look at another example. This sequence, 3, 4, 6, 10, 18. Oh, I think I have something here. Let me see. Oh yeah, so this is the sequence. All right, so let's go to the next one. So the next sequence is 3, 4, 6, 10, 18, 34, 66, etc. So what's the recursive formula for this sequence? What's the formula for this sequence? It's very easy to define F1 is equal to 3, right? F1 is equal to 3. And then what about F2? So you can see F2 is 4, right? You have to find the relationship between these two. And you have to find F3 is equal to 6. You have to find the relationship between these two. You have to find the pattern. Okay, and some students find the pattern already. So you can see it is like, so the difference here is 1. The difference here is 2. The difference here is 4. The difference here is 8. The difference here is 16, etc. Right? It's double the difference of the previous one. So basically, this is something like Fn is equal to what? 2 Fn minus 1 minus 2. Okay, so this is F1 is equal to 3. And you can try. F2 is equal to what? F2 is equal to 2 times 3 minus 2, right? Because Fn minus 1 is 3. So basically this is 4. And my F3 is what? Is 2 times the previous one is 4 minus 2, which is 6, right? And my F4 is 2 times the previous one, which is 6 minus 2, which is 10, okay, etc. So if you see the difference between the two consecutive numbers is double of the previous one, it's most likely is either double or triple, or you can find some pattern. In this case, usually it's kind of some k times Fn minus 1. Okay, usually you will find some Fn equals to k times, oh, my handwriting is terrible, k times Fn minus 1 plus some c. Okay, so that is the answer. Okay, so I'm going to provide you answer. So this is the first. This is still the first recursive formula. You can see it's a linear one. It's a linear line. Okay, it's a linear one. And if you plug in the second one, so I wrote some code. I wrote some code to generate those points, and you can see this one is, what does that call? What does that call? It is actually
exponential.
Yes, it's no, it's not exponential. It is actually it's something like this. Okay, it is something like this. It's like 2x squared, something like this. Maybe minus 2. Okay, maybe something like this. So you can plug in. Maybe it's not. You can plug in maybe plus 3. This is plus 3, plus 1. Yeah, something like this. So it's not exponential. It's like it's a polynomial. Okay, it's a polynomial. All right.
Okay, so this is the some examples from the math. Okay, so now let's look at another recursive formula. I have 0, 1, 1, 2, 3, 5, 8, 13, 12, 21, 34, and 55. What's the next number? What is the next number? If I give you a sequence like this, what is the next number? 89. Yeah, I got a minute. Yeah, it's really quick. It's 89. Why? Why it is 89? What does this sequence call? What's the name of this sequence? What's the name of this sequence? Okay, so this sequence is called Fibonacci. Anybody hear of this? Fibonacci. It is Fibonacci. Fibonacci. How to spell Fibonacci? Fibonacci. So this sequence is called Fibonacci sequence. All right. So this sequence is Fibonacci sequence. And yeah, actually, yeah, you are correct. And if you want to write the Fibonacci sequence, it is like f1 is equal to 0, and f2 is equal to 1. So this is my base case. Instead of I have 1 base case, now I have 2. I have 2. I have 2, right? The f1 is equal to 0. My f2 is equal to 1. And now my fn is equal to fn minus 1 plus fn minus 2. Basically, every term is the sum from my previous 2. Okay, so every term, every number here is the sum of my previous 2. This 8 is equal to 3 plus 5. And this 34 is equal to 13 plus 21. Okay.
Finding f1, how would f negative 1 look?
Oh, in this case, this is my start point. I do not have f. Okay, I'm using the math. I do not have f0 and I do not have f minus 1. So this is my base case. So in this case, my n must be greater or equal to 1. Okay, in this case, my n is greater or equal to 1. So this is my smallest number, 0. This is my second number, 1. And later, I just define this formula. So this is the recursive formula, okay? Because I'm using the previous 2 terms. I'm using the previous 2 terms to come up with a new sequence, okay? So this is called, come on here. Okay, so this is the formula, and this is called Fibonacci sequence. All right, this is Fibonacci sequence is very, very powerful. It's very, very powerful. I can give you some examples. Where is my examples? Okay, so for example, so you probably see this pattern before. So first I have a unit square here. Okay, the side is 1. Okay, and then my side is like 2. And then I can write a side of 3 here. All right, and then I have this is side 3, and now I have a side, and the side is 5. Okay, and then this is 8, so you can do something like this. So this is, and in our daily life in nature, you will see a lot of pattern like this. I can give you like, have you seen this? You can see the pattern in this vegetable. Okay, you can see the pattern here. Another funny thing is, if you use this number divided by, if you use this number divided this number, okay, you're using fn divided by fn minus 1. All right, so I'm going to give you this as a homework. If you use fn divided by fn minus 1, you will find out something very interesting. Okay, so this number, because you have many numbers, okay, when the n increase, this number will reach to some constant. Not exactly constant, but we are very close to some constant. Okay, and anybody know what this c is? Anybody know what this c is? If I use fn divided by fn minus 1, let's say I'm using f like 1000 divided by f 999. This number will be very close to a constant number. Anybody know what this constant number is? This constant number is 1.618. Okay, or something. Okay, or something. All right. So does anybody know this number? What's the name of this number in math? It's called golden ratio. It's called golden ratio. All right. Yes, this is called golden ratio. So it's very interesting. So the Fibonacci in our daily life and in the natural, we have a lot of patterns like this, because this is very beautiful number. 1.618 is like golden ratio, is very popular number. Okay, so you will see some examples. Okay, I'm not going to spend too much time on those things, and I'm going to continue. All right, so okay, pay attention, recall the Fibonacci. This is not Fibonacci. This one is not Fibonacci. We need the base case, okay? Oh, we need the base case. So this is Fibonacci. We need the base case. F1 equal to 0 and F2 is equal to 1. And then we can use the recursive function. Okay, so this is called the base case. This is very, very important. Every recursive function must have at least one base case. All right, must has at least one base case. In some case, we have two, we have more than one. For example, Fibonacci has has two base cases. All right, if you do not have the base cases, the recursion will like continue forever. All right, so this is very, very important. All right, okay. And now I'm going to introduce two things. One thing is called top-down. How do we calculate the Fibonacci? How do we calculate the Fibonacci? So for example, I have this Fibonacci definition. What is F5? What is F5? How do we calculate? First, we use the top-down. We use the top-down method. What does that mean? So for example, I want to calculate Fibonacci 5. I need the Fibonacci 4, right? We need the Fibonacci 4 and the Fibonacci 3. We need these two lines. We need these two terms. Then how do we find the Fibonacci 4? I need the Fibonacci 3 and I need the Fibonacci 2. How do I calculate Fibonacci 3? I need the Fibonacci 2 and the Fibonacci 1. Okay, and now for the Fibonacci 2, I know the answer, right? And for the Fibonacci 2 and Fibonacci 1, I know the answer. So I start from the top. I start from a big number. So this is my problem. My n is what? My n is 5. This is my problem. I can divide this problem to some smaller sub-problem. So this is very important. We divide this problem into two sub-problems, smaller sub-problem. Actually, this is also my problem, right? My problem is Fibonacci n, right? And now actually the n is 5. N is 5. So now my problem size is 5. And I have to divide this problem into two sub-problems. This sub-problem has a smaller size. This sub-problem has smaller size, which is 4. And this problem has smaller size, which is 3, right? I'm using a top-down methodology to calculate the Fibonacci 5. All right, if I give you F100, you have to do the same thing. You have to build a very, very, very big tree, a very deep tree to find F1 and F2. So this is called the top-down. This is called the top-down. Once you reach to the bottom, okay? Once you reach to the bottom, we can calculate further, okay? But at the beginning, we are using a top-down. Yeah, we are using a top-down strategy, okay? It is top-down strategy. And this is important because we may need to see some problems later. And in coding, we have a lot of problems like this. This is top-down. And another way to calculate this is called the bottom-up. The bottom-up. Okay, how do we calculate F5? How do we calculate F5? What we can do is we know F1 is 0. We know F2 is 1. Okay, instead of we start from F5, we just calculate F3. We know F3 is F2 plus F1, which is 1. We can calculate F4, which is the sum of the previous two, which is 2. We can calculate F5, which is, am I right? Which is 3, right? Am I right? Or I'm missing something? Yeah, I think that's right. Okay, so we can calculate the F5, something like this. So this is called the bottom up because I'm starting from the bottom. I'm starting from the bottom. And then I do the other way. I have the F0 and F1. I'm getting, this is 0 and this is 1. I'm getting F2. Okay, I'm getting F2. And this F3 is F2 plus F1. I know the F1 is. Then F2 plus F1, I can get F3. Then the same thing, F3 and F2. I need a table. So this is the table. I need a table to memorize all my previous results. This is very, very important. I need a table to memorize all my previous results because every single one except the first two, I don't know the answer at the beginning. I need to calculate the answer for each one. And I need a table to store those numbers. And then for the next one, I can just look up into this table and fill in this table, right? I'm going to fill in this table from the bottom. So basically, I need two things. The first thing is I start from the base, and then I'm filling the table. And every next number, I just look into this table, I look up this table and calculate and get my numbers and save this number into my table. And I just repeat this process. So this is called the bottom up. I start from the bottom and then I calculate back through the tree. Okay, back through the tree. I'm using the bottom up method to calculate the Fibonacci. Okay, so this is very important. So later I'm going to show you some code. Okay, let me show you the code right now. Let me show you the code. Okay, so this is Fibonacci. So, all right. So this is the Python code. I think many of you understand this Python code. Okay, so first I have to check whether this n is equal, is greater or equal to 0. It's called the input validation. And if n is less than 2, I'm going to return. Is this correct? Anyway, I'm going to return 1. Okay. If okay, that is because 0, 1, 1. So I ignore this 0. I ignore this 0. I start from this 2. But this is very, very similar. It's okay. All right. So if n is less than 2, I return 1. And then I call this Fibonacci 1. Then the Fibonacci 1, n minus 1 plus the Fibonacci 1, n minus 2. Okay. So this is the recursive call. So this I define a function. And inside this function, I call myself. All right. So I'm going to get this one and I'm going to get this one. But very importantly, I need a base case. This is my base case. All right. So this is my function. Is anybody, do you think this function is correct? Do you think, let's see, do you think this function is correct? Yes, but slow. Okay, that's great because you answered my next questions as well. This question, this is correct. This is correct, perfectly correct. Because if I calculate Fibonacci 5, I got 5. If I calculate Fibonacci 10, I got 55. This is correct. But what's, because yeah, some students may hear this term, some students may not hear this term, but it is called, okay. It is running very, very slow. It is running very, very, very slow. And do you know the, if you hear the term, that's great. What's the time complexity for this code? Like 3 lines for code, 3 lines. Actually, I can remove this line because it's just the input validation. What's the time complexity for this piece of code? Yeah, I got some correct results. So this time complexity is actually 2 to the power of n. 2 to the power of n. It's very, very, very slow. It's almost the worst case you can write the code. Although this code is like 3 lines of code, 4 lines of code, but it's really slow. I can just show you really quick. So this now I calculate Fibonacci 10. I'm spending 500 mus. So if I change to 20, it spends 5.5 milliseconds. If I change to 30, okay. It takes like still less than 1 minute. It still takes less than 1 second. If I change to 40, okay, I'm sorry. It takes maybe 30 seconds or maybe 40 seconds. So 40 is not a big number, but it takes, you can see, it takes really long. Probably it takes like 30 seconds or 40 seconds. All right. It probably will take 30 seconds or 40 seconds. Why? Because I'm going to explain later. It's taking let's wait for like 30 seconds and see how long it's gonna take. So this is running my computer. My computer is not too bad. I have like i7 Intel CPU and my memory I think is 24 gigabytes. Okay, so my computer is pretty fast. Okay, but it still takes really long. It still see, it takes 45 seconds, almost 46 seconds, and I get the number. It is really run very slow. And many students ask me, okay, but probably you can upgrade your hardware. Maybe you can buy a new CPU. Maybe you can install more memory. It doesn't help too much. It doesn't help too much. Let's see. I can buy like, let's see, I can buy maybe $10,000 US computer. Or if I'm super rich, I buy like $1 million US computer, and it is 100x faster than my current one. Okay, but it still doesn't solve the problem. Why? Let's see. 2 to the power of 40, because I said the time complexity is 2 to the power of n. If it is 2 to the power of 40, is about what? It's about 1 trillion. Okay, 2 to the power of 10 is 1,000. Okay, 2 to the power of 20 is around 1 million. 2 to the power of 30 is about 1 billion. Okay, so that's how many calculation you need. And the 2 to the power of 40 is about 1 trillion, because every time you increase 10 here, you add 3 0 after this number. Okay, even you increase my computer speed 100 times faster, this is just divided by 100. It doesn't change much. Okay, it is 100 times faster, but 1 trillion divided by 100, it's still a huge number, right? This is only 40. If I increase to 2 to the power of 50, I guarantee it will spend like days to finish this code. If you change to 2 to the power of 100, probably to the end of the whole world, you still cannot get the number. Okay, so that's why this is really slow, because this one is using a top down. As I said before, this one is using the top down, because if I want to calculate F40, I need to calculate F39, and I need to calculate F38, and I need to calculate etc. until I reach to F1. Okay, and for this one, for example, this is F2, right? And then this is F3. After I get the results for F2, I still need to get the results for F1, and for F4. For this, let's see, for this F39, after you calculate the left tree, you still need to calculate the right tree. You need to spend almost the same amount time for the right tree, and this is the same thing. After you finish the F39, you need to calculate the F38. So this is why it is like a tree. It is like a tree. It's like binary tree. So it is taking forever. So the time complexity for this tree is 2 to the power of n. So the top down, usually the top down is slow in recursion. Not usually, but all the time. Okay, if you use the top down methodology, it is slow. If you do not do any optimization, it is very slow. Okay, so the top down, if you are coding in the top down way, it is very slow. So how about we use the bottom up way? Let's try the bottom up. What is bottom up? The bottom is we know the F1, we know the F2, and then we calculate F3, we calculate F4, we calculate F5. How? We just write a for loop, right? We just write a for loop. Okay, and how about my F3? My F3 is this one, and this one is equal to my previous, the bigger one. Okay, and my bigger one becomes the sum of the previous two. Okay, my smaller one equal to the bigger one. My bigger one become to the sum of these two. For example, this is my smaller one, this is my bigger one, and this number is what? This number becomes, okay, this number becomes to A, and this number becomes to A plus B, right? And then this number becomes A, this number becomes to A plus B. So it is using a iteration method to calculate what is F3. F3 is equal to F1 plus F2. And then I store this number somewhere. Okay, I store the number somewhere. And when I calculate F4, I stored F2 and F3 already, and I can calculate F4 directly by looking up F2 and F3, etc. So what's the time complexity of this method? What's the time complexity of this method? And you can see here, I wrote here. The time complexity for this method is big O of n, okay? It's O(n). So now I try to calculate Fibonacci 4000. Okay, I calculate the Fibonacci 4000. You can see. Oh, sorry, I haven't run this cell. It takes no time. Okay, it takes no time to get this number. All right, it is really, really fast. It is really, really fast. All right, so usually bottom up is better. It's faster than the top down. All right, yeah, using the recursive one is so I can also use the recursive one for the Fibonacci, but I need to do some optimization. In this case, I do not have them optimization, it is slow because for every single tree, every single leaf, I have to calculate. Okay, I have to calculate the node in the tree. For every single node, I have to calculate. So that's why it is 2 to the power n. But I can do some optimization. Okay, I can show you the code later how to do the optimization for the top-down approach. All right, so this is basically the top-down approach and the bottom-up approach. Okay, so let's go back to the slides. Let's go back to the slides. Where is this, my slides? All right. Okay, so this is the, I'll show you very quick the code. It's the bottom up and the top down and the bottom up. So let's compare the top down and the bottom up. So top down is a recursive problem solving approach, right? Fn is equal to Fn minus 1 plus Fn minus 2. Okay, so it is using the recursive one, right? It's using the recursive one. But bottom up is usually an iterative one, writing a for loop or while loop. Okay, so the recursive is like it's a recursive call for the top down, and the bottom up is iterative. All right, so the top down usually I'm going to split the bigger problem to the sub problem, a smaller sub problem. Okay, and then I'm going to solve the sub problems using the recursion method. Once I reach to the end, okay, because the recursion method has a base case. Once I reach to the base case, I'm going to do the bottom up. Okay, I'm going to do the bottom up. But if you choose the bottom up, which is using the iterative way and to solve each subproblems, smaller subproblems. Okay, so that's the difference. And the top-down approach is usually easy to implement. For example, if I know the Fn is equal to Fn minus 1 plus Fn minus 2, this is very simple. It is recursive one. It is very easy to implement, right? If you look at my code, it's like a couple of lines. It's very short. Okay, it's easy to implement and it's human friendly. But in bottom-up approach, usually you need to define a for loop. Okay, you need to define a for loop or while loop to do it. Okay, that's the difference. Other part is top-down is usually slow. Okay, usually slow than the bottom-up approach. And another thing is this is kind of advanced topic, but I think some of you know that already. So for example, if this is my F5, let's say I have function, this is F5. So every time I call the F4, I'm going to create some memory. I'm going to use some memory, okay? I'm going to create some memory and not create. I'm going to use some of the memories, okay? And then this is F4. And when you F4 calling F3, so in the memory, it will allocate some memory for F3. And I should put in this way. It will allocate some memory for F3. So when F3 calling the F2, it will allocate some memory for F2. And the same thing here. If you need call F1, it will allocate some memory, will allocate some additional memory, something like this. So in Python, so those things is stored in the stack. You probably now at this moment you don't understand that this is stack, but it's okay. So those things will stored in the stack, which is in the memory. Every time you're going to create a stack in the memory, all right? Use some memory, allocate some memory for every single call. Okay, in Python, the stack size you cannot reach 1,000. You cannot exceed 1,000. So that means for every single recursion in Python, the only thing, the biggest number you can call the recursive function is like around 1,000, not exactly 1,000, but around 1,000. Okay, if you have a very big number and you want to call the recursive way in Python, you cannot do that. The Python forbids you to run a very, very deep recursive function. All right. Okay. And in Java do not have this limitation. C++ do not have this limitation. But again, because every recursive call, it will allocate some memory. So it is possible you get out of memory issue. You can get out of memory because memory is a limited resource. If you use all the memory, you're going to get some error. All right, so be careful. And after this F1 finish, because you have a base case, after this F1 finish, it will free the memory. Okay, it will free the memory and return the number to F2. Okay, it will free the memory. So you have a small memory to use. Okay, it will free the memory and return the results to F2. And then F2, once the F2 is finished, it will return the results and then will free the memory for F2. The same thing here. After the F3 return, it will free this memory. After this F4 return, it will free the memory. All right. In Python and in Java, you do not need to worry about those memory. But in C++, you have to free this memory by yourself. Okay. In Java and in Python, you don't need to worry about those memories. The system, the Python and the Java system will free this memory for you. But in C++, you have to remember free those memory by yourself. Otherwise, you are going to get out of memory issues, errors. All right, so those are very important for the top down and the bottom up. All right, so let's continue. So in general, if you can write an iteration way, write an iteration, write the for loop. Otherwise, yeah, if you can write an iteration, use iteration. And if you cannot use recursion, it's okay. Okay. So let's see some examples in the ACSL contest. I have like 3 or 4 examples here. So this is from the previous contest one. So every year the contest is similar. So you can just practice. You can just practice them. So for example, it's 6:45. I still have some time. Okay, I may go through two problems. Okay, so for example, this one. So this is also a recursive function because the fx is calling fx minus 2 and fx minus 1. Okay, but it has some condition. It has some condition. And this one is our base case because if the x is equal to 3, I can get the results directly. Okay, here, this one is my base case because I do not need to recursively call myself. Okay, so let's see. At the beginning, it is F10. F10. Which one? Let's call this case 1, case 2, case 3. Which recursive call I should call for F10? Okay, I should call the case 1, right? So the F10 is equal to what? Is equal to, I should go because x is greater than 7. So I should go here. This one is called F8 plus 3, right? This one is F8 plus 3. Now my task is to calculate the F8. So I have to calculate F8. So F8 is still go with case 1. So F8 is equal to F6 plus 3, right? F6 plus 3. And then you continue. And then you continue. I'm going to do this. Yeah, I'm going to do this. And I have several examples. I'm not going to go through every single one. So then my F6, I have to calculate F6. F6 goes to the condition 2, which is, right, F5 minus 1, okay? And then I have to calculate F5 is equal to F4 minus 1 because it still goes to the case 2. And my F4 is equal to F3 minus 1. And then my F3. Now F3 falls in the case 3, F3 equal to 9, right? So now I reach to the bottom. So this is which I'm using the top down or I'm using the bottom up. Which methodology I'm using? It's bottom up or it's top down? Yeah, I'm using the top down. Okay, I calculate from F10, I top down. I reach the base case, F3. Now I have to plug in this number. This F3 is equal to 9. I have to plug in this number. This number is to 8. And this number, I have to plug in this number. This number is 7. And I have to plug in this number, which is 6, right? And then this is 6 plus 3 is 9. And this is 12. Okay, so this, then first I reach to the bottom. Then I have to go up and I get the final answer. So this number is 12. Okay, it should be very straightforward, but just to be very, I remove my handwriting. Just to be careful because you always have this plus 3 and the minus 1. sometimes students forget about this because, for example, this F10 is equal to F8 plus 3, right? And then F8 is equal to F6 plus 3. So remember, when you calculate F8, you need to plus 3. And when you plug in this number, you need another plus 3. Okay, sometimes students only plus 3 once, but here you need to plus 3 twice. Okay, just be very careful about this. Okay, so this is our first example. So the second question is similar. So this question is similar. It's a junior contest. If you are in the middle school, you will see some problems in your short problems contest one. Okay, also I have 2 intermediate contests. Intermediate contest, it's very similar. Okay, it is very similar. The only thing, it may have some complicated function. So this is kind of complicated function. So where y, so this is the function. Okay, use the bracket. This is the function. Returns the greatest integer less than or equal to y. So actually, you just be very careful. When you reach to here, you just return this. For example, if I have, if fx plus 2 is equal to like 14, all right, then you are using 14 to divide it by 3. What does this equal to? I have this function. What does this equal to? You can see returns the greatest integer less than or equal to y. So which is 4, right? Because it's less than or equal to y. So which is 4. Okay, so just be very careful about this. Okay, so this is how you should solve those problems. Okay, you will see those problems in contest 1 if you haven't finished the contest. Okay, so the last question is also from the intermediate contest. It's a little bit different, but actually it's the same. So you have F20 here. So what you have to do is you apply this function once. What is F20? Okay, F20 is even number, and then you have to calculate. This is 20 minus 2 is 18, is F9 minus 1, right? F9 minus 1. Yeah, I think this is correct, right? F9 minus 1. Okay, and then you have to calculate F9. F9 is F9. 9 is odd number. You're equal to what? Is equal to 18, right? And then you apply. So this is equal to 17. You apply once. You apply once because F20 now is equal to 17. You apply once. And now the next step is I'm going to apply twice. I'm going to apply this function twice. So basically F20 is actually equal to F17, right? Because you just plug in this number. This number is equal to 17. You just plug in this as 17. You apply this function again twice. It's kind of a recursion way. It's another recursion way, okay? And then you calculate this 17 is equal to a number. And then you apply, let's see, I call this A. And then you apply this 3 times. Okay, then you apply this 3 times. And this one you get is A. And then it becomes to FA. And then you continue. And here you have 1, 2, 3, 4. Okay, you apply this function for 4 times. You just repeat this for 4 times and you will get the results. All right, so this is the contest problems, the example contest problems. So you should receive my email, the sharing document. You should be able to see all the previous year context, and you can do more exercise if you want. Okay, let's have some fun. Okay, we have 10 more minutes. Let's have some fun. Okay, so the first question is you are climbing a staircase. It's a very simple one. Okay, so this one is a very simple one. You are climbing a staircase. It takes n steps to reach the top. So that means I have a stair. I have n stairs. 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5. Okay. So that's add more one more. I have 6 stairs. So this n is a parameter. Okay, so let's say we have n stairs. And each time you can either climb 1 or 2 steps. So you start from here. Each time you can like climb 1 steps or you can climb 2 steps. Your own choice. You can step 1 or you can step 2. Okay. In how many distinct ways can you climb to the top? Okay. In how many distinct ways you can climb to the top? So for example, if you have only 1 stair, it's very simple. You only takes one way. You have only 1 way. If you have 2 stairs, you have 2 way because you can step 1 and step another one. This is the first way. The second way is you step 2 steps directly, right? You have 2 ways. And this is the three stairs. How many ways you have? You have 3 ways. Okay. So now it's n. If it's n, so let's see. I have 100 stairs. I'm not saying 100. I have 10 stairs. Okay. I have 10 stairs. How many different ways you can climb from the bottom to the top? So this is the question. So let's just say 10. Okay, you have 10 stairs. How many different ways? So I got 2 answers. So let's see if I have 4 stairs. How many ways I have? If I have 4 stairs. So the first way, oh, this is 3 stairs. I should have one more. I should have one more. Okay. So this is the 4 stairs. So this is the one way, right? This is number 1. So basically it's 1, 1, 1, 1, right? 1, 1, 1, 1 for 4 stairs. And the second way is I go 1, I go 2, I go 1, right? The first time I go 1 step, second time I go 2 steps, third time I go 1 step, right? The third one is, the first one I go 2 steps, the second one I go what? I can go 1, I can go 1, right? I can also go 2 and 2, right? I can also go 1, 1 and 2. Okay. So I have 5 ways for 4 stairs. So how about F10? So how about F10? I got some correct answer. I got some correct answer. And why? Yeah, I got some correct answer. And why? How do you think about these problems? So now I got correct answers. But how do you come up with this number? It's based on your observation. You find some pattern, and based on the observation, or based on some real analysis. Yeah, either way, because when we deal with those problems, observation is very important. I agree. Observation is very important. If you can find the pattern, you probably can solve this problem. But on the back end, we need to understand how do we analyze those problems. How do we analyze this problem? Okay, this is what I think. This is how I solve those problems. Let's call this problem Fn. All right? I call this problem Fn. What's this problem? What's this problem? The whole thing, the whole red is Fn. What's the subproblem of this blue one? Right? The red is called Fn. What's the problem for this blue one? So this blue one is what? So the red one, the problem size is n. What's the problem size for the blue one? What's the size for the blue one? Anybody?
-1.
Yes, it's Fn minus 1, right? So for the red one, and I have a blue one, I split this bigger problem into a smaller size, Fn minus 1. Okay, if now I'm standing here, how many ways I can starting from here to here? How many ways? Only one way, right? Only one way. Because if I'm standing here already, I can only take 1 step to reach the top. So basically, if I know the answer of Fn minus 1, so that means I solve the problem of n minus 1. I solve the problem of Fn minus 1. I'm standing right here. Then the number of Fn is same as my number of Fn minus 1. Is that correct? If I'm standing here. So this is one way. And what's this? What's this? What's the green one? The green one is Fn minus 2. Okay? The green is Fn minus 2. So that means if I'm standing here, how many different ways I can start from here to here? How many different ways? 2. I got numbers 2. But think about this. If I take one step to reach here, then my solution is what? I have duplicated solution because I solved this problem already. Okay? If you take one step, this problem is actually Fn minus 1, and I will get duplicated results. Okay? If I take one step, I'm going to get duplicated results because I solved Fn minus 1 already. That means I cannot take one step from here to here. Otherwise, I'm going to get duplicated results. So that means if I'm standing here, to avoid duplicated results, the only thing I can do is I'm going to take 2 steps. All right? I'm going to take 2 steps. So that means if I'm standing here, to avoid duplicated records by take one step and another one step, I have to take 2 steps directly. And the number of different ways here is, if I'm standing here, will be the same as Fn minus 2. Will be the same as Fn minus 2. Okay? Then, do I need to consider this? I'm going to use another color. Do I need to consider this one? I do not need to consider this one. Why? If you're standing here, if you take one step, that is same as this solution. If I take 2 steps, this is same as this solution. Okay, so that's why I'm not going to consider this, because this is actually a sub-problem of this one and this one, right? And they have the overlap. So I'm not going to consider this one. So that means my Fn is equal to Fn minus 1 plus Fn minus 2. Okay? That means if I know the solution from here to here, how many different ways? This is the solution Fn minus 1. If I know the solution of Fn minus 1, it will take same number of ways from here to, it will only take one way from here to here. So the number of different ways from here to here to here is same as from here to here, right? That's one solution. And another solution is same. If I know the answer of here, then my number of different ways starting from step 1 to the n is same as I go to the n minus 1 first, and I take 2 steps to reach the top. So this is my formula. And some of you got it correct. This is Fibonacci sequence. All right. So this problem is actually Fibonacci sequence. Now you can solve F10 by using an iterative method, okay, instead of the recursive one. So how do we solve this problem? You have 2 ways. The first way is observation. So you can see this is 1, 2, 3, and you can draw 4 steps. You figure out it has 5 ways. And you draw 5 steps. You can figure out it has 8 ways. Okay, then probably you draw another one, you will find the pattern. After you find the pattern, you can solve it. That's one way to do it. And another way is I'm using the top-down analysis. So most of the time, we are going to do the top-down analysis first. Okay, and then we can use the bottom-up to solve this problem. All right, we can use the bottom up to solve this problem. So this is first question. And what time? 7:03. Okay, so we have another question. It is, I'm going to leave this as a puzzle. Okay, this is another puzzle. So basically you have, let's see, you have a kitchen. So this kitchen, the size of this kitchen is n by 2. Okay, so this size is always 2. And this n is a perimeter. Okay, so this is the kitchen. So let's see, my kitchen is 5 by 2. My kitchen is 5 by 2. And I'm going to put the tile in my kitchen. I can put the tile horizontally like this, or I can put my tile vertically like this. Okay, I can put the tile in different ways, either vertically or horizontally. All right, then I'm going to ask how many different ways I can put the tile in my kitchen. Let's say my kitchen is 2 by 10. My kitchen is 2 by 10. How many different ways I can put my tile? So for example, I can put this way, I can put this way, right? I can put another this way, I can put this way, I can put this way, something like this, right? How many different ways I can put my tiles in my kitchen? Let's say my kitchen size is 2 by 10. Okay, so this one is easy. And you are not happy with those easy questions? I have an insane hard one. All right, I have an insane hard one, and probably you'll spend so much time. You don't need to solve it. It's really, really hard. Even for a college student, even for a master student, this question is really, really hard. All right. So, but you can take a look. How about the only thing difference is 3 by n. It's 3 by n. So it is not NP. Okay, it's not NP problem. Yeah, it's not NP problem. All right, it's not NP problem. You still can use the same methodology to solve it, but it's really hard. All right, so this are some fun for you guys. All right, but you can think about this. This one is easy. This one is too difficult. Okay, this one is insane hard, too difficult. All right, so that's all for today's lecture. So any question? All right, okay, so if you do not have the question, so that's all for today. I'm going to send you the PowerPoints to your email. And probably I will put this into the share. Okay, just to check the share drive. All right. Okay, thank you. Thank you very much.
Bye.
Yeah, bye.
Thank you.
Thank you.
Bye. Thank you.